time for some more quantum mechanics. One-dimensional time-independent Schrodinger equation. I'm working through a bunch of problems and I already did this one. So this is an infinite square well, one-dimensional infinite square well with a step. Let me show you my previous solution because we're going to do it again. Because it's nice to have this, like, you know, these different methods that you can use to solve these kind of problems. So the last time I did this, I did the shooting method. And the basic idea was to solve this differential equation starting here and then just finding out where you end up over here. And if you don't meet the boundary conditions, then start over. Let me show you how that works. And then we're going to do this we're going to use the finite difference method after that. This is the code, and I will put a link down below to the whole video on this. And let me make this a little bigger because bigger is better, don't you think? So the basic idea is just use the Euler method to solve this problem. I need to start with an initial energy. I need to start with an initial derivative of psi, and then I can calculate the second derivative and use that to find all my other values. That's what I did. And that's all this stuff here. And I'm not going to go over all the details because you don't want to see that. You want to see, watch the video. When I play it, I change the energy until I get it. And the most important thing is what is that final energy? And I get 8.85. And it's just an approximation because it depends on my energy steps and my space steps and all that stuff. Let's do it again. And we're going to start on paper. Going back to the paper. This is my one-dimensional time-independent Schrodinger equation. And here we have a function for u. We're going to have to deal with that. And I did this before, but it didn't have a step. But it's useful to do it again. So really quickly, how do we use the finite difference method? Imagine that I take 1, 2, 3, 4. I break this into 5 values of psi. Psi 0, psi 1, psi 2, psi 3, psi 4. And I define these as spread out by delta x. They're all delta x. And I want to find the first derivative at this one right here. Let's just call it psi I. So psi I prime, the derivative, is delta psi over delta x. But if I go from 1 to 3, this would be psi I plus 1 minus psi I minus 1 over 2 delta x, because I'm going that whole limit right there. If I want to take the second derivative, psi I double prime, I'm going to use the derivative halfway derivatives. So the derivative halfway here would be psi 2 minus psi 1. This would be psi 3 minus psi 2. And then the change in distance is delta x. So this will be equal to psi, right here, I plus 1 minus psi I over delta x minus, then before that, psi I minus psi I minus 1 over delta x. All of that over delta x. And if you just do a little bit of algebra, psi I double prime, I get over delta x squared. I have psi I plus 1. Then I have minus psi I minus psi I minus 2 psi I. And then I have minus psi I minus 1. So it's plus psi I minus 1. And that's my derivative. It depends on the value before it and the value after. So with this, I can write down the Schrodinger equation like this. Negative h bar squared over 2m. And the derivative for psi I, I'm going to write this as psi I plus 1 minus 2 psi I plus psi I minus 1, all of that over delta x squared. That's that. Then I have plus ui psi, that's a psi I, equals e psi I. So ui, every value that I have a psi, I have a potential. So I do have u's. I have u's, right? Now, this is a bunch of equations, right? These are linear equations. And if I don't include, I can't do this for all the psi's. I can't do it for psi 0 because I don't have a psi negative 1. I can't do this for psi 4 because I don't have a psi 4 plus 1, 5. But that's fine. I can do it for the middle ones. And if you do that, and I'm not gonna go into much detail because I did this before, we can write this as the following equation. And I'm going to write it a little bit messy, and that's fine. I'm going to write this as the matrix. See, I have a negative 2 psi I multiplied by this over delta x squared. That's going to be equal to h bar squared over m delta x squared. Now the next term is going to be equal to this one, I plus 1, is just going to be this times that, negative h bar squared over 2m delta x squared, and then I get a 0, and then I get all these are zeros. This term down here is going to be negative h bar squared over 2m delta x squared. And then this term is going to be the same. Oh, minus u. I forgot. I got to factor out. So it's plus u. Plus ui. That's all right there. H bar squared over m delta x squared plus ui. And this is another negative h bar squared over 2m delta x squared. And then down here I get 0, negative h bar squared over 2m delta x squared. I get this term right here. I'm just going to 0, 0, 0, 0, 0, 0, 0, 0, zeros. So that's my matrix right there. And I went through this in a little bit more detail in my last, I'll link it down below, finite difference method using the eigenvalue problem. But I have this matrix, I'm going to call that H. If I do that, I turn this problem, and I have my values for psi 1, psi 2, psi 3, as far as I want. I don't include the first psi 0, which is 0. I don't include the last one, which is 0. That's why I have these zeros there. And then this is going to be equal to E, and then those same vector values for the size. This becomes an eigenvalue problem because if I call this matrix the Hamiltonian H, which it makes sense, I have H psi equals E psi. This is the eigenvalue problem. Eigenvalue. And it basically says what vectors psi can I operate this matrix A, H on it and get back the same vectors with a constant E. So if I solve this, I'll get a list of vectors at work along with their eigenvalues E. And that's exactly what I want. That's what I want to do. And that's what I'm going to do. So how do you do this in Python? Well, we're going to have to use some of the features in numpy. Some people call it numpy, which is probably right. But I like to call it numpy, and so I'm going to. Okay, where'd I put my thing? Here. So I am using Jupyter Notebooks because I need to use real Python. I normally like to use web vPython, but it doesn't have matrix operations in there. You could probably make it work, but I don't want to do that. So there's two options you can go to, and I'll put a link down below, Anaconda, and you can download and install web vPython. Or you can use Google Colab, which I've done before too. And I just want to use Jupyter just because it looks a little bit different and it's the same thing. So Google Colab is Jupyter Notebooks, but it's online. You can use your Google account to get there. So I'll just putting print x just so, because there is no x, just to see what kind of size it looked like. I want to make sure it's big enough. So the first thing I'm going to do is to import two important modules, numpy and matplotlib. Import numpy as np, import matplotlib.pyplot as plt. I'm going to run that cell. So one of the nice things about Jupyter Notebooks is broken into cells. You can run just a cell. You can rerun that one cell. You could put in text in between the cells. It's really nice. If you haven't used it before, it's pretty nice. I'm not a super expert with this kind of Python. I'm not really an expert with other stuff, but I do my best to get it to work. And so sometimes I do things a little bit differently than other people do, and that's fine. That's what makes it fun. Let's start off with our constants. I have h bar equals 1, m equals 1, a equals 1, u0 equals 10, n equals 10. So n is the number of pieces I'm going to break this into. And that's the first thing I need to do is to make my list of x values. I'm going to make my list of x values. Python has, numpy has these arrays that are really nice. So we can make an array of numbers and then use them as a number. It's really kind of cool. So to do that, I can just say x equals mp.len space for linear space. And I say what number do I want to start on, what number do I want to end on, and how many pieces. So let's start at a 0 to a with n pieces, and I'm going to print that. And you'll notice I do get 10 numbers there, but I don't, that's not what I want, right? I wanted 0, 0.1, 0.2, 0.3, 0.4. So I can do that if I do n plus 1, because this is printing 0 is the first one and 1 is the last one, and then the rest of the thing split up. It's not 10, so I want to add one more element in there. So I can just do that with n plus 1, and now I'll get what I wanted. Okay. Now, the next thing I want to do is to make my dx value, my delta x. And there are a lot of ways you can do this, but you could try to say, well, it should be 0.1, right? Yes, but I like to just do it this way. I like to say dx equals x1 minus x0. The second value of x minus the first value, that is literally dx. That's what delta x is. And you can print that if you want. It's always nice to print these things to test. Print dx, print dx. Is that, 0.1. Is that big enough for you? Let's see if I make it a little bit bigger. That's better. I feel a little bit better. Okay. Now I need to make my u values. I need a list of potentials, and it should look like 0, 0, 0, 10, 10, 10 if I get to halfway. But I don't want my u's to be the same size as my x's. And I'm actually going to need another list of x values. I want a list of x values that don't include the first one and don't include the last one, because I'm not changing those psi values, so I want to match it up with my size. Here's what I'm going to do. I'm going to call it xp for plotting x, because I'm going to use this to plot. np.len space, and I want to go from dx to a minus dx. So dx, a minus dx, and I don't want n minus 1, I want n. I mean n, no, I want n minus 1, right? I don't want to include the first or last ones. And let's print that out. So now it does not have 0, it does not have 1. And my window is a little bit bigger than your window, and what's going to happen is I'm going to type stuff that you can't see. There, fix that. Great. Now I want my u's to be the same, look like that too. I'm going to just make it the same. np.len space, that's right, space, dx, a minus dx, n minus 1, and let's print that. I always like to print things to make sure. And this is also why I have n equals 10. Because if I get it to work with n equals 10, I can see it, and then I can make it bigger later, and it's not a big deal. So that's good. Now let's go through and change my values of u. Here's what I'm going to do. For I in range, length of u, print I. And I've done this in Python, other Python. So it goes 0, 1, 2, 3, 4, 5, 6, 7, blah, blah, blah. Now I can use that to set my values of u. I equals 0. And that'll make them all 0. But I don't want them all 0. I want to go through, and if my x value, I can use the same index, is greater than a over 2, so halfway, then I want it to be equal to u0. So if xpi, I'm not using x because that goes from 0 to 1. I don't want to include those n's. If xpi is greater than a over 2, then ui equals u0. Now let's print u. And it goes 0, 0, 0, 0, 10, 10, 10. And you see this, I have this problem. This middle one's a 0, and it should be, I don't know, 0.5 or 5 or whatever. And there is a function in numpy that can make these step functions. It's called the Heaviside function. But I always forget how it works, and I like making it my way. So I'm going to do it this way. And if you want to use the Heaviside function, you can do that. Okay, so now I have my x's, I have my plotting x's, I have my u's. I need to make my Hamiltonian function. So let's make the Hamiltonian function down here. H, and I'm going to build it in pieces because you can make a mistake. You want to build these things in pieces so that you know if you make a mistake. There is a built-in function in numpy that makes a diagonal matrix. It's called np.diag, not surprising, hopefully. And I just need to give it, say, well, how many values do I want and which they be. So I'm going to use another function, np.ones, which just gives ones, and I need to tell it how many. And I want n minus 1. Remember, my total space is n plus 1. So n minus 1 will leave off the end and the beginning, and that's exactly what I want. And we can print that. Print h. And it's a 9 by 9, because I have 11 data points, and the middles are 1s. That's exactly what I wanted. Except that's not what I wanted. I want the middle one. I'm looking at my equation right here. It should be h bar squared over m delta x squared plus u. That's fine. We can fix that. Let's do it one thing at a time. H bar squared divided by m times dx squared times, I'm just doing that part. And yeah, you can say, well, h is 1. Why even doing h bar squared? Because if I ever change it, it's the same. So I fix that. Now I need to add my u. And this is part of the magic of Python. I can just say plus u. Since u is the same size as n minus 1, I can just add that in there. And let's just check. Look, here I have my diagonals hundreds. But down here, these should be 110, because plus the 10 potential. And there you go. It works. See, we can see that it's working. 110, 110, 110. Yay. Now I need to do my next diagonal. Plus np.diag, np.ones, n minus 2, 1. So I don't want n minus 1. I want 1 fewer. So 1, 2, 3, 4, 5, 6, 7, 8. Not 9, 8. And I'm just going to, and I have to tell it where to go. So that diagonal with the 1 says do 1 row up. So that should put all these as 1s. There. Now they're all 1s. I don't want them to be 1s. I want them to be negative h bar squared over 2m delta x. So let's multiply that. Negative h bar squared divided by 2 times m times dx squared times run. I think that's right. Now I need to do the next one down, which is the same thing but a negative 1. I'm just going to copy this. Copy, Control C, paste, Control V, and then change this to a negative 1. There. There's my matrix. Got it. Now, one of the things, if you don't want to print it, I don't want to print it because it's going to get big. I can print the shape. Print h.shape, and that will just tell me what it's a 9 by 9. That's what I wanted to do. We're almost there. Let's calculate the eigenvalues and vectors. E psi equals np dot linear algebra. It's a module in the module. Eig h, and then I just give it the matrix I want to find the eigenvalues for, which is h. Let's just print out two things. Print E0. It's going to have a whole bunch of E's. I just want the first one. And I want the first psi. Print psi 0. So there's my first energy level, which is a little bit different than what I got. Right? I got 8.85, but I only have 10 spaces. And that really shifts where the middle part is. And my eigenvectors are wrong, because those are that's a row of my eigenvalues. But I actually want the vector is the column. So I can print out the column by taking the transpose psi.t and then printing out the first 0. So those are my values of psi that I want. And they're all positive, which makes sense. We're done. We have it. Okay. Now let's go through, and I don't want to print that because that's going to get big. Let's switch it up to 100 in. So I'm going to go back up here. I'm going to change in to 100, and I need to rerun the cell. So you can press play, just so you know. Shift Enter runs too. I've always pressed Shift Enter because it's a lot quicker. Now I need to rerun this cell because I need to make a new H matrix, and you see it's 99 by 99. That's good. Now I need to rerun this, and you see I get 8.65. So we're basically right there with the same eigenvalue as before. Let's go ahead and plot my wave function. I'm going to make a simple plot. plt.plot. My x values is xp. My y values will be psi.t0. I'm plotting the first one. And I'm going to turn the grid, plt.grid. I like the grid. And let's give it a label. plt.xlabel is x. plt.ylabel is psi. And it's upside down. Why is it upside down? It wasn't upside down before. Let's change this back to 10. They were all positive values before. That's that. And I'm going to print out my values. See, these are all positive. Now they're right. That was weird. Why were they negative? 100. Run this one. Run this one. Fine. See, they're negative. That doesn't make any sense. Oh, no, that's right. Psi t0. And that's going to be negative. XP, well, let's do 50. That's negative. Let's do 20. Why? Isn't that making sense? Does it make sense to you? Wait, that one didn't change. Oh, I did that. That's 10. That's 20. That one's positive. I mean, that looks similar to what I had before. Let's just look over here. 0, I did do 0 to, I use the same values. DE, A is 1, U is 10. That's really strange. And I don't want to waste a bunch of time. It's probably something silly. I do want to normalize this and plot the probability density. So that's what I'm going to do next. And then I'll leave the error, my probably dumb error, as a homework assignment. You know, one of the things when you work through these things live, it's very easy to make a mistake and not see it because you're like, I got to do the video. I got to keep plowing forward. So there's very good chance that there could be an error. And I could redo the video, but I think it's worthwhile to see that errors do happen and give you a chance to find it. I think that's good for you. I think everything is mostly good. I'm getting the same kind of energies, right? What is the energy I'm getting? 8.28. Yeah, so I think it's pretty good. I'm still thinking. Okay, so let's normalize this and replot it. I can normalize the wave function by integrating over the whole space of psi star psi. I can do that very simply as I equals np.sum, and then I just say, what am I going to add up my sums? I'm going to add up the sums of arrays. I'm going to say psi squared times dx. So psi squared I know to say which one. Psi dot t 0, the first one, squared, times dx. That's my integration. Now, to get the value of a, I'm just going to take 1 over the square root of that. A equals np dot square root 1 over I. Now I can plot a times that psi, and that should be normalized. So I just put a times, and there's my normalized wave function. Let's plot this. Let's just square that, and that'll be the probability density. No. Well, I lost a parentheses. Okay, there it goes. There we go. Now let's just plot the second one too, because why not? I think the second one has the normalization constant that's the same, but let's just check. I equals np dot sum psi dot t 1 squared times dx. A equals np dot square root 1 over I. plt dot plot xp a times psi dot t 1 squared. Yep. And there you go. Now, here's something cool, right? Is the object more likely to be found on the step or not on the step? So that first energy level, let's print out the second energy level. Print E2 equals, which would be E1. And you notice it's 25, so it's a greater energy level than the step. And the first one was not. It's less than the step, so it has to tunnel into the step. Is it more likely to be found on the side without the step or with the step? And the answer is with the step. And if you think about it, it's sort of like a hill. If you have a ball rolling, once it gets uphill, it's going to be going slower. So on the step side, it's going to be going slower, so you're more likely to find it where it's going slower than faster. That's why this bump over here, it has a higher probability on that side than this side. And you can keep doing this for all the other energy levels too. Let's actually do it for energy level 3. I'm just going to change this to 2, just so I don't have to retype everything, and run that one. That one is surprisingly equal. Well, there you go. Okay. Finite difference method, infinite square well with a step. I'll put links to those other videos, like I said, down below. Hopefully that helps. I'll talk to you later.